तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we will study the matrix representation of the simplex algorithm. We will also derive a couple of equations that we will be using later in sensitivity analysis. We take the familiar example, first do the simplex iteration and then explain the matrix method of solving it. Problem is to maximize 6x1 plus 5x2 subject to x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, x1 x2 greater than or equal to 0. Let us quickly set up the simplex table and solve this problem. We have 6x1 plus 5x2, we start with x3, x4, we have 1, 1, 1, 0, 5, 3, 2, 0, 1, 12, 5, 0, 0. Variable x1 enters, we compute the values of theta. So we have 5 and 4, so variable x4 leaves, this is the pivot element. I have x3 and x1 here. Zero, 1 by 3, 1 minus 1 by 3, 1, 1, 2 by 3, 0, 1 by 3, 4, Cj minus Zj will be 1 minus 2, 24, variable x2 enters. Now theta is 3, 6, this leaves pivot element x2, x1, we have 0, 1, 3, minus 1, 3, 1, 0, minus 2, 1, 2, that equal to 27, we have 0, 0, minus 3, minus 1. Now, when we solve this problem using the simplex iteration, what do we exactly do in every iteration? Suppose we take an intermediate iteration that is shown here. The first thing we are interested in is whether this is optimal. So in an intermediate iteration, the first thing that we want to do is to find out the Cj minus Zj's for the non-basic variables. And if all the Cj minus Zj's are less than or equal to 0, then it is optimal. And then we compute the value. It is enough if we compute the value of the objective function after we have found out that it is optimal. If it is not optimal, then all that we need is what is the entering variable, and what is the leaving variable. So essentially when we have, this is the first thing that we would like to compute. The moment we know in an intermediate iteration these are the basic variables, and we will also have corresponding values here, we do not need to compute this entire matrix. We need to compute the Cj minus Zj's, only these two numbers, these would be anyway 0 corresponding to the basic variables. So we need to compute these two Cj minus Zj's, and if one of them happens to be positive, it enters, or if both are positive, the maximum enters. Then we need to find out the leaving variable, for which we need this column corresponding to the entering variable. And then since we have the right hand side, we compute the theta, and at the end of this iteration we know what are the basic variables in the next iteration. So now these are the basic variables in the next iteration, and then we realize that we have to compute these Cj minus Zj's. Now both of them turn out to be negative, we get the optimum. So we do not necessarily require computation of this matrix, which we end up doing in our tabular form. Therefore, can we work out the simplex in a different way, by which we do the minimum required number of computations and not end up computing this entire matrix. For example, if after adding the slack variables in every iteration we have, if we have m constraints and n variables, we actually compute an m plus 1 by n plus 1, because there are n variables and a right hand side, we have m constraints and a Cj minus Zj. So in every iteration we compute an m plus 1 into n plus 1, whereas what we need are the n minus m values of the non-basic Cj minus Zj's, plus we need m values of the right hand side, plus we need m values of the entering column, plus we need one value at the optimum of this. So while we need only this much, while we need m plus n plus 1 values, we end up computing a matrix which is m plus 1 into n plus 1. Now can we redo the simplex in such a way that we compute only the required number of elements of this in every iteration, and in the process learn a couple of equations which we will use in sensitivity analysis later. So let us go back and start the simplex in what is called as a matrix representation of the simplex. So we have the first iteration, we have, now we define the set of basic variables x3 and x4 is now defined as a set xb, a set of basic variables. So we have x3 and x4 here, and that is equal to the right hand side value, which is 5 and 12. Now we have to check whether this is optimal. To do that, we need to find out values of Cj minus Zj for variables x1 and x2. So we need to compute C1 minus Z1 and C2 minus Z2. These are the two things that we need to compute. Now we are going to write one equation which we will derive a little later and show how that equation holds, but right now we will use that equation to get the values of Cj minus Zj. We are going to call every column of the given problem as p bar j. Now p bar j represents column corresponding to variable xj, and then the moment we define an xb, we also define something called a basis matrix, which corresponds to the p bars, that is, we define pj as the column in the original matrix, and then the basis matrix B is now obtained from the pj's corresponding to the basic variables. So in this case the basis matrix will be p3 and p4, which is 1 0 0 1. For variable x3 the corresponding coefficient is p3, which is 1 0. For variable x4 the corresponding column is 0 1, which is our P4. So because x3 x4 are basic variables, B is made out of P3 and P4 in the order in which they appear as basic variables. So the B matrix is this. In this case, the B matrix turns out to be an identity matrix. So B inverse is also I in this case because B is I. We are going to use one equation, which is this. In any intermediate iteration of the simplex, for example, if we are here, then corresponding to the variable x2, this column in an intermediate iteration is given by p bar j, and that p bar j is going to be defined as B inverse Pj, where B corresponds to the basic variables of that iteration. If we are looking at this iteration, then the basic variables being x3, x1, the corresponding B will be 1 0 1 3. So B is defined for a given set of basic variables. So once we define a set of basic variables here, any column in the intermediate simplex iteration will now be given by p bar j equals B inverse Pj, where Pj will be for this is P2. So p bar 2 equal to B inverse P2. This is p bar 2, this is P2, this is xB, for which the basis matrix will be 1 0 1 3. We can invert it and then we can actually prove that this is B inverse P2. But right now we assume this. Now assuming or granting this, any Cj minus Zj for any j, the way we compute is, for example, the way we computed this C2 minus Z2 is, we first computed Z2, which is the dot product of this and this, 0 into 1 by 3 plus 6 into 2 by 3, which is 4. So it is the dot product of this and this. So this we call as CB. CB is the coefficient, objective function coefficients corresponding to the basic variables. This case 0 6 because of this 0 and this 6. x3 comes first, x1 comes later. So CB will be 0 6. So your Zj is nothing but it is the dot product of CB and p bar j. So this is Cj minus dot product of CB and p bar j. This is Cj minus CB B inverse Pj. We now write the CB B inverse as y, and we write it as Cj minus ypj, where y is CB B inverse. Now for this problem, this is B and CB is 0 0 because basic variables xB are x3 and x4, corresponding to them the values in the objective function are 0 0, so CB is 0 0. So in order to find Cj minus Zj or C1 minus Z1 equal to C1 minus yp1, I need to find out a y. Now y is CBB inverse. Pre-multiplying, I have yb equal to CB. In this case B is I, so y itself is CB equal to 0 0, because CB is 0 0, y is 0 0. So C1 minus Z1, C1 is 6, 6 minus yp1 1 3, which is 6. Now C2 minus Z2 is 5 minus 1 2, which is 5. Now the variable with the most positive Cj minus Zj enters, so x1 enters. Now to find out the leaving variable, we need to find out, which is shown here, x1 enters. We need to find out the column corresponding to the entering variable. So we need to find out a p bar 1, which is B inverse P1, B inverse is I. So, in this case P bar 1 is 1 comma 3. Now, to find out the leaving variable we need to find out a theta, as we did in this case. We have got this 1 comma 3, we have the right hand side equal to 5 comma 12. So, we need to find out theta such that, now there are two ways of doing it. One is we can say that we want to find out the minimum theta, which is 5 divided by 1 and 12 divided by 3, the minimum one will be 4, which is what we have seen here. The other way of doing is to find out minimum theta such that 5 minus 1 theta is greater than or equal to 0, 12 minus 3 theta is greater than or equal to 0. The same values 5, 1, 12, 3 are being used. Either we can say theta as the minimum of 5 divided by 1, 12 divided by 3, or saying that we want to find out minimum theta such that 5 minus theta is greater than or equal to 0, 12 minus 3 theta is greater than or equal to 0. This would give us theta equal to 4. Now, because the second variable gives us theta equal to 4, x4 leaves the basis, and the new set of basic variables are xb will be, x4 leaves the basis, x1 replaces. So, you have x3 x1 as you have here x3 x1. Interestingly, you can now go back and write the actual values of the right hand side by doing this. The second one went out. So, this will not, this will, if you substitute theta equal to 4 here, you would get a 0, but the value here is not 0, but the value of theta itself. So, you will get theta here, and for the other one you can substitute 5 minus theta is 1. So, the second iteration, the solution is base set of basic variables are x3 x1 with solution 1 comma 4. So, we have x3 x1 with 1 comma 4. Now, we have CB corresponding to x3 x1 will be 0 comma 6. The basis matrix B corresponding to x3 x1 will be 1 0 1 3, 1 0 1 3. Now, we need to check whether this is optimum. To do that, we need to find out the Cj minus Zj corresponding to the two non-basic variables x2 and x4. So, we need to find out C2 minus Z2 and C4 minus Z4. Now, go back, Cj minus Zj is Cj minus Ypj. So, we need to find out y. To find out y, we need Yb equal to Cb. So, we need to find out a y such that y1 y2 into 1 0 1 3 is equal to 0 6, from which y1 plus 0 y2 equal to 0. So, y equals, this gives y1 plus 0 y2 equal to 0, from which y1 is 0, y1 plus 3 y2 equal to 6, from which y2 equal to 2. So, we have computed our y. Alternately, we could have found out B inverse for this, and then we could have written y equal to CB B inverse, and we would have got this. Let us, for the sake of completion, compute the B inverse and keep it. Now, what will be B inverse for this? Now, determinant B will be 3. Now, cofactor B will be 3 0 minus 1 1, adjoint B will be 3 0 minus 1 1, and determinant and B inverse for this will be adjoint by determinant 3 by 3 1 minus 1 by 3 0 1 by 3. This will be B inverse. and then we could have found out y by using this equation y equal to CB B inverse. So 0 6 into this would give us 0 into 1 plus 6 into 0 0, 0 into minus 1 by 3 plus 6 into 1 by 3 is 2. We would have still got the same B. So we do not need any of these now, we have got our B inverse alone here. So we have found out our y. So C2 minus Z2 equal to, C2 is 5 minus yp2, which is 5 minus p2 is 1 comma 2, coefficient in the constraint corresponding to variable x2 is 1 comma 2. So this will be 0 into 1, 2 into 2, 4, 5 minus 4 is 1, and C4 minus Z4 equals 0 minus 0 2 into 0 1, because P4 is 0 1 from the coefficient matrix. So this will be 0 into 0, 2 into 1 is 2 minus 2. Now variable x2 with a positive value of C2 minus Z2 enters. So I have variable x2 enters, and then what is the leaving variable? Now we have to find out a leaving variable. So we need to find out p bar 2. Now p bar 2 is B inverse P2 because we have the equation p bar j equal to B inverse Pj. B inverse is 1 0 minus 1 by 3 1 by 3 into P2 1 2, this is 1 into 1 minus 2 into 1 by 3, 1 minus 2 by 3 is 1 by 3, 0 into 1 plus 2 into 1 by 3, 2 by 3. Same 1 by 3, 2 by 3 is what you see here as 1 by 3, 2 by 3, B inverse P2. Now we need to find out a theta for the leaving variable. This is the right hand side, 1 and 4. We need to find theta such that 1 minus 1 by 3 theta is greater than or equal to 0, and 4 minus 2 by 3 theta is greater than or equal to 0. This would give theta equal to 3, this would give theta equal to 6, minimum value is 3, which happens for the first one. So you realize that the first variable x3 leaves the basis. Now the next iteration, we write it here. Now xb is, now x3 leaves the basis, x2 enters the basis, so we have x2 x1, and the value of the right hand sides can be got by substituting the theta. Now this is the equation from which we found out theta, so the value will be theta here, which is 3, and here the value will be 4 minus 2 by 3 into 3, 4 minus 2, which is 2. So we have a solution x2 equal to 3, x1 equal to 2. Now we need to find out b corresponding to x2 x1 as it appears. So x2 is 1 2, x1 is 1 3, so you have 1 2 1 3, CB the objective function coefficient corresponding to x2 x1 as they appear, so 5 and 6, and then we need to find out a B inverse. In order to find out y is CB B inverse, so we need to find out B inverse. Let us find out B inverse by the normal method. So determinant B in this case will be 3 minus 2 1, cofactor B will be 3 minus 2 minus 1 1, adjoint B is the transpose of the cofactor, so 3 minus 2 minus 1 1, and B inverse is adjoint by determinant, so we just write the B inverse here itself, from which B inverse is adjoint by determinant is 1. So, 3 minus 2 minus 1 and 1. So, this is the value of the B inverse. Now, we have to find out y such that y equal to CB B inverse, which is 5 6 into 3 minus 2 minus 1 1, which is 5 into 3 15 minus 12 3, 5 into minus 1 minus 5 plus 6 1. Now, we have found out y. Now, to verify whether this is optimum, we need to find out C3 minus Z3 and C4 minus Z4. So, C3 minus Z3 is 0 minus C3 is 0, Z3 is y P3, which is 0 minus 3 1 1 0, P3 is 1 0, which is here. So, this would give us minus 3. C4 minus Z4 is 0 minus yp4, which is 0 minus y into 0 1, p4 is obtained from here. So, you would have 3 into 0 plus 1 into 1 minus 1. Since both C3 minus Z3 and C4 minus Z4 are negative, the algorithm terminates with the solution x2 equal to 3, x1 equal to 2. Now, we compute the value of z. Z is equal to CB XB, which is 5 6 into 3 2, which is 27. Now, this algorithm terminates. Now, what we have actually done by calling it the matrix method is we have exactly worked out the simplex iteration, but we have understood how the Cj minus Zj's are represented in terms of the Pj's and the Y's and so on. We have also done something more. We in all these, now what happens in the matrix method is, if you look at the equations carefully, the P2 keeps appearing again and again. Now, for example, we have now shown that the values here in every intermediate iteration is actually dependent on the problem data. In the normal simplex tableau, the way we created the simplex tables, every subsequent iteration was actually dependent only on the values of the previous iteration. We did not look at these values. Now, what we have done in the matrix method is, we have represented every iteration now in terms of only the first table of the simplex or in terms of the problem. That is one change that we have made. Secondly, we have also done a lot of computations. Now, we have to see whether this is better or the original simplex with n minus m into, or this is better. Now, what did we do? In every simplex iteration, what did we do? Here, we evaluated a right hand side. So, we found out m values of the right hand side to begin with, and then we evaluated the y. Y is a set of dual variables. So, you will have as many dual variables as the number of primal constraints. So, you have another m values of y, but to calculate the y, we needed the B inverse. So, we said we look at plus B inverse, and the moment y is calculated, we calculated Cj minus Zj for the non-basic variables. How many non-basic variables do we have? We have n variables, out of which m are basic. So, n minus m Cj minus Zj's we calculated. We identified one entering variable, and then we calculated the numbers corresponding to the entering column, which is plus another m numbers. So, we effectively did this m and this m will get cancelled, 2m minus n plus the effort on the B inverse. Now, what is the effort on the B inverse is the first question, and second very interesting thing that we will see, can we read the B inverse also from the simplex table? The answer is, we can read the B inverse from the simplex table. Let us look at this. In the very first iteration we said B is equal to I, B inverse is equal to I. The second iteration, this was the B inverse that we computed, 1 0 minus 1 by 3 plus 1 by 3, and you will find that your B inverse is here, 1 0 minus 1 by 3 plus 1 by 3. In the third iteration, your B inverse 3 minus 2 minus 1 1, you find your B inverse here 3 minus 2 minus 1 1. In the first iteration, B inverse was identity matrix, you find the identity matrix somewhere here. Now B inverse is seen under the identity matrix of the original table. Now B inverse is always seen right in the simplex algorithm under the identity matrix corresponding to the original table. Therefore, when we said that we computed B inverse, we also computed another m square terms, because B is a square matrix which is m by m, we computed another m square terms. So now here we have computed m plus 1 into n plus 1, here we have computed 2m plus n plus m square, and we will realize that this is actually smaller than this. Therefore, the matrix method is advantageous over the regular simplex method. Now why do we have the B inverse under this? The answer is, in every simplex table what we actually do through our row column operations is we are actually performing one iteration of the Gauss-Jordan method. Now the moment we identify that x3 x1 is the basic variable, which means x2 x4 are non-basic, we do certain row operations from the previous table so that we get an identity matrix corresponding to x3 and x1. What was 1 0 1 3 in the previous, after some row operations, has become 1 0 0 1, but we continue to do the row operation along all elements. Now the moment we get this identity matrix for this, which is what we do in the Gauss-Jordan, we can straight away read the solution from the right hand side, which is what we do. So what effectively we do is we start with the 1 0 1 3, which is the basis matrix corresponding to x3 x1, and then do a set of row operations to get it into the identity, which means if this is B corresponding to x3 x1, 1 0 1 3 is B, then we do the row operations to make it into I. How do we do that? Effectively we are pre-multiplying it by the B inverse. So in some sense, from this, when we get this part of the simplex table, this is obtained by consistently pre-multiplying every column by B inverse, where B is 1 0 1 3. In the process, this identity matrix also gets pre-multiplied, and that is why you see B inverse always happening under this identity matrix. Similarly, when we have this iteration, we know the basis matrix is x2 x1, so we start with 1 2 1 3. Even though we have done some row operations here and then some row operations here, effectively we have carried out a set of row operations to get a 1 0 0 1 here, which means effectively we have pre-multiplied every column of this with the B inverse corresponding to the B 1 2 1 3. So in the process, the identity matrix also gets pre-multiplied by B inverse. So B inverse is always seen under this. Now not only are we pre-multiplying this identity, because we are pre-multiplying every column with B inverse, any P bar j is B inverse Pj. Therefore we have proved the result, P bar j is B inverse Pj. Once we know this result, Cj minus Zj equal to Cj minus Cb P bar j is obvious, from which Cj minus Cb B inverse Pj, this comes from the dot product, substituting for P bar j, this is equal to Cj minus Ypj. So the important things that we have learnt from the matrix method are these. We can also, this is the first equation and the most important equation that we have learnt. This is the second equation, Cj minus Ypj or Cbb inverse, y equal to Cbb inverse is another equation. And straight away, now in every iteration what do? We are actually solving in this case for Bxb equal to the right hand side. So, when in this iteration what we are trying to solve is, when we fix x2 x1 as the basic variables, we are going back and we are trying to solve for x2 plus x1 equal to 5, 2x2 plus 3x1 equal to 12. So, we are solving effectively for bxb equal to b, or we are trying to solve in this case for x2 x1. So, 2 1 x2 x1, so 1 2 1 3 into x2 x1 equal to 5 12. So, we are trying to solve for bxb equal to b, from which xb equal to b inverse b. This is another equation. So, we will be using this equation, we will be using this equation, we will be using this equation, we will be using this equation when we do sensitivity analysis. Now, at the end of the matrix method, we have now found out a way which can be slightly faster than the tabular form of the simplex and would give exactly the same results that we have. We have also learned that B inverse appears in the simplex table. So, in some sense, if we look at a simplex iteration, we see lot more in the simplex table than what we would want to or we would have imagined. We see the primal solution here, we see the value of the objective function here, we see the entire dual solution here, we also see the B inverse from here. So, a simplex table tells us almost everything about the problem that we are trying to solve. Now, the next thing that we would see is what is called sensitivity analysis, and we would be using these equations that we have seen right now in our sensitivity analysis. So, let us begin sensitivity analysis immediately. Now, at the end of it all, let us go back and explain sensitivity analysis again through an example. Now, what do we want to see in sensitivity analysis? Now, every linear programming problem is characterized by an objective function a right hand side value, coefficient matrix. Now, in the simplex table, the objective function value comes at the top, the right hand side values are shown here, and the coefficient matrix is shown in this way. Now, let us assume that we have a linear programming problem that we have just now solved. Now, after solving it, we would like to see how the solution would change if there are some changes in some of these numbers, or some changes in these numbers, or some changes in these numbers. Now, what will happen to the optimal solution if there is a change in the objective function coefficient? What would happen to the optimal solution if there is a change in the right hand side value? What would happen if there is a change in the coefficient matrix? We would also like to do a couple of other things. Suppose I add another variable into the problem, and along with the variable comes its objective function coefficient and constraint coefficients. What will happen? Does the present solution remain optimal or would it change? Suppose I add another constraint to the problem, and along with the constraint comes a right hand side value as well as the coefficients. Now, with the addition of the new constraint, does the problem continue, or does the solution continue to be optimal, or is there going to be a new solution? Now, all these questions we would like to address. An obvious answer to all these is make the change and solve the problem all over again. Now, that is a very, very obvious answer to the question. If after solving a problem we realize, for example, that a certain 5 on the right hand side becomes 6, what happens to the solution? One would always go back, change the 5 to 6, solve the problem all over again. but is that the most efficient and intelligent way? Or alternately, can we use the information that we have, can we use the optimal solution that we have, and then from the optimal solution can we proceed to evaluate all these changes. Now that is done in what is called sensitivity analysis. Now in sensitivity analysis we will be seeing a few things. The first thing we will see is changes in the objective function coefficient, change in objective function coefficient for a non-basic variable. Because the optimal solution has a set of variables which are our basic variables. So we would like to see if there is a change in the objective function coefficient of a non-basic variable, what happens. 2. If there is a change in the objective function of a basic variable. 3. If there is a change in the right hand side value. 4. If there is a change in the coefficient matrix, in the constraint coefficient corresponding to a non-basic variable. 5. Adding a variable to the problem. 6. Add a constraint. 7. Constraint coefficient for a basic variable. Now we look at each one of these by considering an example here. The example that we would have is this: to maximize the example would be to maximize 4x1 plus 3x2 plus 5x3 subject to the condition x1 plus 2x2 plus 3x3 less than or equal to 9, 2x1 plus 3x2 plus x3 less than or equal to 12, x1, x2, x3 greater than or equal to 0. We first assume that we have solved the problem. So we take you through the steps of the simplex algorithm to solve this problem. We quickly go through this. We start with slack variables x4 and x5 because they are less than or equal to constraints. So the first simplex table can be seen here with x4 and x5 as the basic variables with objective function coefficient 0, right hand side values 9 and 12, Cj minus Zj's are 4, 3 and 5. So variable x3 with the most positive Cj minus Zj enters, theta is computed as 9 divided by 3 is 3, 12 divided by 1 which is 12, 3 is minimum theta, variable x4 leaves the basis and variable x3 enters the basis. So next iteration would be starting with x3 and x5 which are here. So we have x3 and x5 which are here, and these are the iterations with Cj minus Zj value 7 by 3 minus 1 by 3 0 minus 5 by 3 0 and Z equal to 15. Now variable x1 with the most positive Cj minus Zj enters, corresponding theta values are 3 divided by 1 by 3, 3 divided by 1 by 3 which is 9, and 9 divided by 5 by 3 which is 27 by 5, 27 by 5 is smaller than 9, So, variable x5 leaves the basis and this is the pivot. So, next iteration would have x3 and x1, we have x3 and x1 with 6 by 5, 27 by 5, all Cj minus Zj's are negative. So, this is 138 by 5. So, this is the solution. We assume now that we have this optimum simplex table along with this, we just write down only the optimum simplex table here. So, we would have x1, x2, x3, x4, x5, right hand side values. So, we just write down the optimum table with x3 and x1 here with values 4, 3, 5, 0, 0, x3 has 5, x1 has 4, and the simplex table would be 0, 1 by 5, 1, 2 by 5, minus 1 by 5, 6 by 5, 1, 7 by 5, 0, minus 1 by 5, 3 by 5 and 27 by 5 with Cj minus Zj values 0, minus 18 by 5, 0, minus 6 by 5, minus 7 by 5 and 138 by 5. Let us assume that we have this solution and we want to do sensitivity analysis on this problem with respect to this optimal solution. So, first thing we would look at is what will happen to the solution if there is a change in the objective function coefficient of a non-basic variable. So, we take variable x2 which is presently non-basic, and if there is a change in the objective function coefficient of this. Now, which means if this 3 changes to something. Now, we call this as C2. Now, let us assume that it is C2. Now, because x2 is a non-basic variable, the x2 does not appear here, so C2 will not appear here. Now, the only place there will be a change, the right hand sides will not change now, because let us go back to our equations. Now, right hand side value is B inverse B, we have not made any change in the B matrix, so right hand side will not change. But Cj minus Zj's are changed. We should also consider this. If this change of this value from 3 to something, if at all it is going to have an impact, now that what will be the impact? The impact would be that the present solution is no more optimal. The present solution would no more be optimal if either the right hand side becomes negative and the optimality is retained, or the right hand side is still non-negative, but the Cj minus Zj's, one of them becomes positive and it tries to enter. Now, the only impact that this C2 can have is in C2 minus Z2. It does not have any impact on the other things, because this is not going to affect y. It is not going to affect y because it is not going to affect Cb. Cb would remain as 5, 4. So, the only change that will happen if there is a change in the objective function coefficient of a non-basic variable, then that will be reflected as a change in the Cj minus Zj corresponding to that non-basic variable. So, C2 minus Z2 is the only thing that will undergo a change. So, C2 minus Z2 will become C2 minus 5 into 1 by 5, 1 plus 4 into 7 by 5, 28 by 5. So, minus 1 plus 28 by 5, this is C2 minus 33 by 5. Now, as long as C2 minus 33 by 5 is less than or equal to 0, the present solution will be optimal because this quantity will be negative. So, the change C2 will have an impact only if C2 is greater than 33 by 5. So, if C2 is greater than 33 by 5, C2 minus Z2 will become strictly positive and variable x2 will try to enter the basis. Now, at C2 equal to 3, we would have 3 minus 33 by 5, which is minus 18 by 5. Now let us look at what happens if the present value would give negative. A value of C2 greater than 33 by 5 would make C2 minus Z2 take a positive value. So if you consider value C2 equal to 7, if we consider C2 equal to 7, for example, if this 3 increases to 7, till it increases to 33 by 5 or 6.6 or 3 and 3 by or 6 and 3 by 5, there will not be any impact of this change. The present solution will continue to be optimal. Only when it exceeds 33 by 7, something will happen. So if we consider C2 equal to 7, then C2 minus Z2 will become 7 minus 33 by 5, which is 2 by 5. So this will become plus 2 by 5, this will become, if this becomes 7, this becomes plus 2 by 5. And because of this 2 by 5, variable x2 will enter the basis. Now we need to find out a leaving variable, and we need to compute theta. 6 by 5 divided by 1 by 5 is 6, 27 by 5 divided by 7 by 5 is 27 by 7, which is smaller. So variable x2 will enter and variable x1 will leave, and we have to do a simplex iteration. Now that is shown here. Now variable x2 will enter and variable x1 will leave, which is shown here. 2 by 5, the newly computed value is shown here. The change C2 to 7 is shown here. So x2 enters and the leaving variable is variable x1. So we do a simplex iteration. We have identified the entering variable first and then the leaving variable. So we do a simplex iteration with x3 and x2 as basic variables that you can see here. And after one iteration, we realize that we have reached the optimal solution with x3 equal to 3 by 7, x2 equal to 27 by 7 and z equal to 204 by 7. In this example, the optimum solution we could reach in one iteration. Sometimes we may need more than one iteration to reach the optimum. But the advantage, for example, is we started with the previous optimum table. We made the change, we made the change in the optimum table and the effect of the change in the same table. And now we realize for this example, in just one iteration, you could get the optimum solution to this problem. So this is how we handle case where there is a change in the objective function coefficient of a non-basic variable. We now look at what will happen if there is a change in the objective function coefficient of a basic variable. Now let us do that once again from the optimum solution of this problem. So we go back to the same table and make the table appear as it did when we started. This was 3, so you have 5 plus 28, 33, 3 minus 33 by 5, which is minus 18 by 5, and this is how the optimum table looks. Now we go to the second part of sensitivity analysis, where we try to see the change, if there is a change in the objective function coefficient of a basic variable. Now there are two basic variables, x3 and x1. We could take any one of them. So we take change in the objective function coefficient of variable x1 to illustrate this. Now which means this 4 will become C1 and this 4 will also become C1. Now once again, there will not be any change in the right hand side value because the basis matrix B is not affected, nor is the right hand side affected. So there will be only changes in the Cj minus Zj's. In spite of this change, x1 being a basic variable will have a Cj minus Zj 0 for that variable, but these numbers will, all the three numbers can change now because they use Cb. Cb has changed, therefore Cj minus Zj for all the non-basic variables will change. So if there is a change in the objective function coefficient of a basic variable, then this will be reflected as change in Cj minus Zj for all the non-basic variables, and all of them have to be evaluated. So C2 minus Z2 will now become 3 minus 5 5 into 1 by 5 is 1, 1 plus 7 C1 by 5 minus 1 plus 7 C1 by 5, which is 2 minus 7 C1 by 5. Now C3 minus Z3 will be C4 minus Z4 will be 0 minus 5 into 2 by 5 is 2 plus C1 into minus 1 by 5, so minus C1 by 5, which is C1 by 5 minus 2. C5 minus Z5 will be 0 minus 5 into minus 1 by 5 minus 1 plus 3 C1 by 5, which is 1 minus 3 C1 by 5. If C1 is such that all three of them are less than or equal to 0, then the present solution would remain optimal. For example, if we substitute C1 equal to 4, you would realize that all of them are negative. But if one of them turns out to be positive, then that variable would enter. So we have to check whether 2 minus, as long as 2 minus 7 C1 by 5 is less than or equal to 0, there will not be any impact. So this would give us 10 minus 7 C1 greater than less than equal to 0. So 7 C1 greater than equal to C1 greater than or equal to 10 by 7. So as long as C1 is greater than or equal to 10 by 7, then this will continue to become negative. Now for the other one, C1 by 5, so C1 greater than or equal to 10 by 7, now C2 minus Z2 is negative. When C1 is less than 10 by 7, now variable x2 will enter, x2 enters. So when C1 less than 10 by 7, this would enter. Now here, okay. Now C1 by 5 minus 2 is less than or equal to 0. So C1 minus 10 is less than or equal to 0. C1 less than or equal to 10, it will continue to be optimal. So this would be optimal. And for the third one, we have 1 minus 3 C1 by 5 less than or equal to 0, 1 is less than or equal to 3 C1 by 5, 3 C1 greater than or equal to 5, C1 greater than or equal to 3 by 5. When C1 is greater than or equal to 3 by 5, this would remain optimum. C1 less than or equal to 10, this would remain optimum. C1 greater than or equal to 10 by 7, this would remain optimum. So let us see this as we go here. We observe that if C1 less than or equal to 10 by 7, C2 minus Z2 can become positive. For C1 greater than 10 and for C1, then C1 greater than 10, C1 minus Z1 is greater than 0, and for C1 less than 3 by 5, C5 minus Z5 is greater than 0. So we realize that in the range 6 by 5 to 10, the present set will be optimal. See, what we need to look at is, as long as C1 by 7 is C1 is greater than or equal to 10 by 7, C1 less than or equal to 10, 3 by 5, the present set will be optimal. So from these three we realize that we have a range. As long as C1 is within the range, C1 is between 10 and, this should be 5 by 3, sorry. So as long as it is between 5 by 3 and 10, it will be optimal. So when it leaves the range, then it will not be optimal and something else will enter. So we try to substitute a value C1 equal to 12, which is beyond the range. So we would expect this one to enter the basis, which means we would expect this variable to enter the basis, and that is now shown in the simplex table, the next iteration. We now realize that when we substitute C1 equal to 12, then we would get 12 by 5 minus 2, which is 2 by 5, which comes in here, So, variable x4 enters the basis and we need to find out the value of the leaving variable. There is only one theta, which is theta equal to 3, and in the next iteration we get the optimum solution. Now, the optimum solution has z equal to 72. So, in summary, if there is a change in the objective function coefficient of a basic variable, then that change gets reflected in the Cj minus Zj's of all the non-basic variables, and then we need to find out the range of the C1 or the coefficient which would keep it optimal, and if the new value of C1 violates the range, then one of the present non-basic variables will become basic, and we continue doing simplex iterations till we reach the optimal. Other aspects of sensitivity analysis we will see in the next lecture.